Welcome back to the solutions of the Schrodinger equation of hydrogen atom. So in lecture 32 today, we will resume the part of solutions of the radial equation of the hydrogen atom. So I hope you remember that this is the radial equation for the hydrogen atom we just derived from the Schrodinger equation in lecture number 32. So this differential equation cannot be solved by any easy method. Okay, so this can be solved by a power series method, and thankfully it can be solved exactly, and all the solutions of the hydrogen atom can be derived directly. So anyway, so if someone solves this differential equation by power series method, we would get the solutions as R and LR. So this is the radial part of the solution, and you see it is dependent on two quantum numbers. So now a new quantum number L is being introduced here. So it's needless to say that L is the principal quantum number, and the L is the quantum number that we are already familiar of from the spherical harmonic part. So the expression for R and LR is quite complex. So you see I have already written it. So this part actually stands as the normalization factor or the normalization constant. So the formula is already there. And this is the variable part with respect to R. And then once again there is another function, L subscript n plus L superscript 2n plus 1, which is a function of 2R divided by N over A naught, N multiplied by A naught. So now the question is, what is the A naught? Okay, so we'll come to that thing later on, but here for the time being we can refer the A naught as the Bohr's radius. Okay, so if you can't remember what is the definition of Bohr's radius, we will come to that point exactly after in the next lecture or so. But for the time being, let's focus on this function. So this function has a particular name. So this is called associated Laguerre function. Okay, so it is almost like the Legendre polynomials, right? You remember it has a Legendre polynomial expression for m is equal to 0, and for a value of m not equals to 0, we have polynomials. Those are called associated Legendre polynomials. So very similar to that, we have this function known as associated Laguerre functions. So similar to our Legendre polynomial, there could be different values of the associated Laguerre functions depending on n and L values. Okay, so like last time, let's take a look about on the first few expressions of the associated Laguerre functions. Okay, so I'm going to clean the board and I'm going to write the first few associated Laguerre functions with the lower value of n and L. Okay, so let's do that. Okay, so as you can see here we have a list of first few associated Laguerre functions. So for n is equal to 1, n is equal to 0, the associated Laguerre function is represented as L1, 1 function of x, and it comes out to be minus 1, and where x is equal to 2r divided by A naught. So we just have followed the expressions from the associated Laguerre functions to denote the superscript and subscript. So remember, the subscript is n plus L and the superscript is 2L plus 1. And this is the new part. That means the outcome of the derivation has been given directly over here. Okay, so we are not deriving it. So we are interested on these results. So this. So similarly for n is equal to 2, L is equal to 0, and L is equal to 1, we have these expressions where x is equal to r over a naught. For n is equal to 3, we have three scenarios, L is equal to 0, L is equal to 1, and 2. And for each of the cases, we have the associated Laguerre functions take up expressions like these. Of course, here x is equal to 2r over thrice of a naught. Okay, so these are the standard expressions or standard formula following which one can deduce what? One can deduce the final psi r theta phi. So remember, now the expression for psi r theta phi becomes is equal to r nl, okay, which is the function of r multiplied by y lm theta phi. Okay, so remember, both this radial part and angular part is a function of L, and the radial part is function of n and L. Okay, and the angular part is the function of L and m. Of course, that means theta and phi. So we have already found out this value, and now we can find this out because we have two expressions. So just few minutes ago I have written the expression for r and r in general. Now to derive r and r, we have the expression for normalization constant multiplied by the associated Laguerre function. So now we have the expression for this. This can be used as a standard table to find out the expression for associated Laguerre functions. So from the formulas in the standard table, one can easily find out. Of course, I have to write n, l, and m here. So psi n lm as a function of r theta phi takes up this value. So from this, one can easily find out what is the expression for psi 1, 0, 0. All right. Or similarly, what is the expression for psi 2, 1, 0, etc. Okay. So we just have to use n, l, and m values. We plug in here, and from the standard table we can derive it. Okay, so let's take a look that if someone correctly puts the values of n and l and m and correctly follows the standard table, then what would be the complete expressions for psi r theta phi for first 2 or 3 cases. Okay, so let's erase the board and let's try to find out those psi's. But remember, it's your job to verify from the standard table that whatever I'm going to write in the next minute, you also get the same result. Okay, this is nothing complicated. You just have to follow some standard formulas or standard table. You have to plug in those values and make sure you get the correct expressions. Okay, so please take this as a simple exercise. Okay, because as a student of chemistry, we must be able to feel, to realize, to able to write the correct expressions of different solutions of Schrodinger's hydrogen atom equation. Okay, so let's try that out. So you must also verify that the first few complete hydrogen-like wave functions as obtained from the standard formulas and expression appear like this. Okay, so here what happens is these expressions have been given in a very generalized manner, and it has been written hydrogen-like. So that means not only for hydrogen, say for any other atoms where Z is not equal to 1, in fact Z is more than 1. For example, for helium, Z should be 2. For lithium, Z should be 3. So Z is the number of protons, means the nuclear charge. So apart from this, the z value number, everything else remains pretty same and can be derived from those standard table. So this is Xi100, Xi200, Xi210, and Xi21 plus or minus 1. So now you see that wherever we have only n value is a non-zero, where L and m value are 0, we do not have any theta phi part. We have only the radial function, radial part. Okay, number one. Number two, whenever we have L value, you see the theta function is coming, cos theta. And for Xi21 plus or minus 1, where L is non-zero value, we have the sine theta part, and then e to the power plus or minus I phi. So if it is 2, 1, 1, it should be e to the power plus I phi, and it should, if it is 2, 1, minus 1, it should be e to the power minus I phi. Okay? So now sigma is equal to Zr divided by A0. So obviously for hydrogen atom, sigma should be R by A naught because Z is equal to 1. So for Xi100, the expression should be 1 over root over of pi, 1 by A naught, 3 by 2, e to the power minus R by A naught. Okay, so these are the final expressions of the solutions or the wave functions of hydrogen atom for different N, L, and M values. Okay. Now, before we proceed, we will quickly take a look at the existing things, that means the orthogonality condition. So how to write a generalized expression for the orthogonality conditions of the different wave functions of the hydrogen atom. Okay, so let's clean the board and let's write that. So the orthogonality condition to test whether two wave functions are orthogonal or not, we have to follow this generalized expression. So we have to talk about the triple integral because we have these three parameters r, theta, and phi. So r varies from 0 to infinity. Okay, and the theta varies from 0 to 2 pi, and phi varies from 0 to pi. Okay, so that becomes Xi star. Okay, so N, L, M, and we have R, theta, phi. This, multiplied with Xi, N prime, L prime, M prime, function R, theta, phi, and then we have the volume element. Okay, so the volume element is R square sine theta d theta. We should write the dr part first. Dr d theta d phi. Okay, so this should be equal to, we have the Kronecker delta expressions. So the Kronecker delta expression should be delta n prime multiplied by delta l prime and delta m prime. Okay, so now from our previous knowledge we have already seen that in any case n is equal to n prime, then this value of the delta should be what? Is equal to 1. And wherever we see that n is not equal to n prime, or n is not equal to n prime, or n is not equal to n prime, so the value of these deltas would vanish, would become 0. Okay. So this is the way to test the orthogonality conditions. Okay, so remember the expression of the element of integration of volume element here, r square sine theta dr d theta and d phi. Okay, so now let's move on to the energy part. So that means now we have the solved wave function, but our Schrodinger equation said that h psi n l m r theta phi should be equal to E, okay, and then r theta and phi. So now the question is, whenever we have solved it using a particular value of NLM r theta phi, we should get an eigenvalue as the energy. Now the question is whether this energy eigenvalue depends on N, L and M. So that means the question is whether the energy of the hydrogen atom is dependent on all the three quantum numbers N, L and M. Okay. So in the next part we are going to find out that what was that energy eigenvalue obtained by solving the Schrodinger equation. Okay, so let's clean that out and discuss it. Before we proceed further, I would like to make a little correction here. So based on our usual convention of the spherical coordinate, this is x, this is y and this is z, this is a vector r, it makes the angle theta with respect to z, and its projection on xy plane makes an angle phi with respect to y. If that is so, then the angle range of theta, if we talk about the theta first, becomes 0 to pi. So that was my mistake. Sorry, I apologize. This should be 0 to pi, and the angle phi, its range is from 0 to 2 pi. So there will be the term 2. So r theta phi, r goes from 0 to infinity, theta goes from 0 to pi, and phi goes from 0 to 2 pi. So that was a little mistake over the expression that I just wrote earlier. So now it has been corrected. Okay, so now let's proceed to the energy expressions obtained by solving Schrodinger equation. Okay, so solving the Schrodinger equation with appropriate boundary conditions, one can get the energy expression E is equal to something like this. Minus mu is the reduced mass, e to the power 4, E is the charge of the electron, divided by 8 epsilon 0 square. Okay, so epsilon 0 is the permittivity in this free space, h is the Planck's constant, and n is the principal quantum number n. Okay, 1, 2, 3, etc. It can take up any value. So what we see here, that this energy is a function of n only, and energy is independent of L and M value. Remember, we are talking about the hydrogen atom only. So what we get, that for hydrogen atom, the energy of the different levels is only dependent on the principal quantum number. It does not depend on the L and M values. So for a fixed n value, all the orbital quantum number or the levels associated with any orbital quantum number or the magnetic quantum number are degenerate. Okay, that is a very important finding from the quantum theory. Okay, so now let's compare whatever Niels Bohr derived the energy of the electron in a hydrogen atom. So he assumed that this is the centrally located nucleus, fixed. This is the electron and orbiting around the nucleus, and this is the radius. Okay, so he told that the radius is fixed, r. So here this a naught is termed as the Bohr's radius. So Bohr's radius is nothing but that r, means MVR of the electron at its the ground state. Okay, so that means the distance of the electron of hydrogen atom, it has only one electron. So at its ground state, that means basically n is equal to 0. N is equal to 1. What is the value of r? So that was the Bohr's radius. So Bohr's original expression involved, instead of mu, it involved m, mass of the electron, because historically he didn't use the reduced mass concept. But except the reduced mass value, everything else was the same. Okay, so that means whatever Niels Bohr calculated from the very classical mechanics, the final expression turned out to be exactly identical. All right, and the thing is, the value of n here that came from the calculation of the quantum mechanics, Niels Bohr used that value n in which context? Do you remember? Yes, he used that angular momentum MVR is equal to mh cross. That means angular momentums are fixed and can take up only discrete values as an integral multiple of h cross. So from where that value n came? Okay, so later we found that this integral multiple of h cross, that constant, took up the role of the principal quantum number n. All right, and also another striking feature is for n is equal to 1, if we calculate this energy, so it comes out to be exactly minus 13.6 electron volt. And experimentally, it has been also found out that this is exactly minus 13.6 electron volt from spectroscopic result verified by the quantum theory. And the most striking feature of the Niels Bohr theory, that this value En calculated from all these constants does also come out to be minus 13.6 electron volt. So now we can realize that how accurate was Niels Bohr's understanding of classical mechanics. Of course, not only classical mechanics, he introduced this part of his own interpretation of quantum mechanics. So it is due to his because Niels Bohr was a genius, and because of his magnanimous scientific vision, he was able to introduce such a radical concept, so that finally the experimental value came out to be exactly identical with the value derived from the quantum mechanics. Okay, so after 32 lectures, we came back to the same point, that whatever Niels Bohr proposed in 1913, especially in the after like 15 years later, or 15 to 17 years later, quantum mechanics concluded the same thing. Okay, but the question is, there were drawbacks from Niels Bohr's theory. So can the quantum mechanics answer those drawbacks? Okay, so we will find it out sometime later down our course and curriculum. But next lecture, we are going to find out the detailed nature of the individual expression of the wave function, that is psi 100, psi 200, psi 210, etc. Okay, so it's time to conclude here for today's lecture. So we will finish this chapter in 1 or 2 more lectures. So you please study the textbook and stay put. So we'll see you in the next lecture. Till then, goodbye.